as a few nanometers. Right. So localized surface plasmons. So I'll begin with this, the same question that I asked earlier. So if you have a bulk metal, the resonance condition is epsilon m equals 0. And then if you have a surface, like a half dielectric, half metal, then the condition becomes half metal, half dielectric equals 0. Okay, so what I asked earlier in our previous lecture was like, what's gonna happen if you go to a particle? Like how much of metal and dielectric portion should appear in this equation? And then you said, okay, so if we put x here, this x must be larger than 1, right? Because there are more dielectrics than metal, if you look at this. And that is true. And then I'll tell you that x is actually 2 in this case for spherical particles. Okay, so let me tell you how do we know it. So I don't want to go through these equations again because we've already done this when we solve for small dielectric particles, when we do a Rayleigh scattering. So this is exactly same lecture notes. So I'll just briefly remind you what we've done. So instead of actually solving a wave equation, if the particle is small, we can just solve for Laplace equation. And then this is called electrostatic approximation. So if you go to the electrostatic approximation, then the solution can be found by using spherical harmonics, which is never going to appear in the midterm exam. Okay. And so you have like all sorts of solutions. And again, these are exactly same equation set and slide that you already saw in small dielectric particle lecture notes. But anyway, what we've done was we try to satisfy the boundary conditions, and by doing so, we determine all the coefficients for the electromagnetic electric potential, basically. So if you, yeah, I just recommend you to just check this slide again if you forgot about this. But what's important is that at the end of this discussion, you probably remember that we have polarization. Dipole moment is proportional to the applied electric field. And by definition, what's appear here is defined as a polarizability, right? So the polarizability was this. And you remember this. This is the exact same conclusion that we obtained in our small dielectric particle lectures. But at that time, we didn't pay attention to this denominator, okay? Because at that time, everything epsilon m and epsilon d were both positive. So we don't need to pay too much attention on it. But now, your material becomes metal, and then epsilon d, dielectric epsilon is positive, then there is a possibility that you can make this thing to be 0, right? And if the denominator becomes 0, your polarizability diverges, right? So this is what's actually happening. So if you, and then here, from here, you got the condition, epsilon m plus 2 epsilon d equals 0. This is the resonance condition for spherical metallic particle. So the factor 2 appears here. And when this condition is met, you can see here the polarizability diverges. But of course, epsilon m is not just a real number, but it has a finite imaginary part, so that it never become a, actually diverges, but it has a peak with certain maximum, right? So what does that mean? So physically, like if you just try to imagine what is happening, you have light coming in with oscillating electric field, and then you have a metallic particle. Okay, and this metallic particle, you have plus and minus charges, and then plus and minus charges try to oscillate along the incident electric field, right? And then due to this oscillation, this particle acts as an oscillating dipole, right? And then this oscillating dipole emits light. This is basically scattering process. So what does that mean by having a diverging polarizability? Is that for the same amount, same intensity of light, your dipole can be arbitrarily strong, right? So for the same field, the charges are oscillating, crazy, so that the scattered light is also increases proportionally, right? So this is what's happening. Like when the plasma oscillation, when the surface plasmon oscillation occurs, these dipoles, even though it's very, very small, it scatters light like crazy, so that the scattering efficiency becomes very high. And of course, it's not infinite because again, because of the finite loss. So this is what we call about the localized surface plasmons. So bulk plasmon, surface plasmon, and then localized surface plasmon resonance. So here the plus and minus charges are oscillating, and then when this condition met, then this oscillation becomes very, very strong, so that it scatters light with a very strong intensity. Yeah, and then from here on, it's just here again how the oscillating electromagnetic dipole, electric dipole, have an electric H field and E field. This is basically the same slide that we saw in our previous lecture material, and yeah, so right. So this is the final slide that I want to talk today, and here we have, where is it? Yeah. So if you actually write down the scattering cross section and the absorption cross section, they have this form. And as you can see, both of these diverges when the denominator becomes 0, right? But the difference is that scattering cross-section is proportional to a to the 6th power. So, but the absorption cross-section is just proportional to a to the cubed. So that if the particle becomes small, then this one more rapidly decays, so that small particles absorption basically dominates small metallic particles. And then for larger metallic particles, scattering dominates due to this different dependence. And then here is what's happening. This is actually, I guess it's a measured data, I'm not sure. But anyway, if you look at the cross-section, extinction cross-section, Well, extinction cross-section is actually absorption plus scattering. And then if you look at the extinction cross-section as a function of wavelengths, then you can see a gold 50 nanometer gold particle in the air, the extinction becomes maximum at 500 nanometers. But if you go to a silica, the extinction occurs at 550 nanometers, right? So now you understand this, because the resonance condition, localized plasmon resonance condition is 2 epsilon d equals 0. So if epsilon d becomes larger, then the matching condition occurs at lower frequency, right? So keep in mind that epsilon m was 1 plus epsilon p squared omega p squared divided by omega squared. And then if this is equal to minus 2 epsilon d, then it's like 1 plus 2 epsilon d is equal to omega p squared omega squared. So as epsilon increases, omega decreases, right? So if your surrounding material becomes more higher and higher index, then your resonance position goes to longer and longer wavelengths, or a lower and lower frequency. Okay, so this is all I wanted to say today.